So, thank you for also letting me to know what has been done. So, I did interact with one of the participant, Dr. Lakshmanan Rao, sir. Yeah. So, thank you very much for the input, sir. There. Yeah. Yes, as Avasti sir has asked me. So, quantum tomography I would cover. Okay. So, what I will do, I think, just to address the state tomography. Okay, that was the topic, I guess, for yesterday. Let me see the topic. Yeah, yesterday the topic was state tomography. I think quantum light state tomography. And today's topic is understanding the state of light from the prospect of probability distribution. That was the topic for today. So, what I will do, right? Today's topic and tomorrow's topic, I have already planned what to be discussed. Okay. So, what I will do is, in a way, actually, I needed some part of today's fundamental to go back and discuss this tomography part.
Sure.
Okay. So what I will definitely ensure is by end of tomorrow, right? Okay. As per the schedule, even tomorrow also, I need to talk about the light distribution, probability distribution. Okay. If I want, like, I have the list with me. Okay, just a minute. Right. Yeah, anyway, it is there. We're not go much into that dwelling of that. So what I will do, yeah, Poissonian distribution, all those things I'm supposed to cover. I'll ensure that the state tomography is covered in the today and tomorrow session. Before before we are going to start the sensing part, I'll ensure that. Okay, right? Fine. Okay, so let's see the number of participants. The participants is 150 plus. We'll start. I think we are 1 minute shy from 2:05. Yeah, Academy has hinted that its recording started. Okay. Right. So yeah, I think people are showing up. Anyway, recording is there, so they may check that whatever is missed in the initial level. Okay, and we will revise also, right? So as usual, I'll use my blackboard writing, and also this time I have not prepared a PPT as such. Okay, because it's more of the theory and some interesting mathematics. Okay, right? So what I will do, I'll discuss neatly with my blackboard writing. Okay, so you people can definitely follow it up later. Okay, if you please play attention, definitely you are going to follow. Okay, so it is not much of a difficulty, even though let me hint you, even though it appears to be some too much of mathematics, it is not actually. If you approach with the positive manner, you can definitely get what I was discussing for today. Okay, right? So we'll just straight away start. Fine. Yeah. So first of all, we need to understand what is the light. Okay, state of light. I do have a lecture notes, but I use my Blackboard notes, a Blackboard, to explain things. Okay. So the state of light we wanted to understand. Okay. Right. So how are we going to approach that? From the prospect of probability distribution. Some distribution of light, how it behaves. Okay. From that prospect, we'll understand. Okay. And what we are is our target for today, or at least for tomorrow, by end of tomorrow, we want to understand what kind of probability distribution is involved in describing the light, which is named after Wigner and it's called a Wigner quasi probability distribution. Okay, that is the target for us for in this today's and tomorrow's session. Okay, right? So if you recollect back, okay, if you recollect, right, if I just take a box, a one-dimensional box, okay, which means if I put something inside, let's say at x is equal to 0, x is equal to L, it's a one-dimensional box. Okay, if I put something inside, it is only supposed to move left and right. Even though I have written as a drawn as a rectangular box, the electron inside, if I am going to put an electron as a particle, a microscopic particle, it's supposed to go left and right, that's all. We have discussed this earlier, and what I see here, if I try to find out what is the location of this electron, and what we saw interestingly earlier, we saw, okay, the position of the electron was shown as some kind of a distribution. You see, this is a position of the electron, and position of the electron is maximum at some point and absolutely zero at some point. Okay, zero presence, okay, and maximum presence, right? So if you get, it's a positive, by the way, it is positive. And see, this is the presence of the electron, right? So we did know that a quantum state of an electron is like alpha 0 plus beta 1 if it is confined to only two states, okay, where absolute alpha square and absolute beta square would give me probabilities. Okay, it gives me probabilities. Okay, now which means alpha and beta are probability amplitudes. Probability amplitudes. Okay, which means the probability amplitudes which can go positive or negative. Okay, probability amplitudes. Why I am talking positive and negative? Because if you just take a wave which goes positive and negative. Okay, so here I have positive things. Let's say if I take a function, let's say function of position x, and then if you just take a square root of that function of position x, and then if you plot that, let's say, let me call this is equal to plus or minus h of x. Okay, what you see is, you see a nice sinusoidal function we see. Okay, let me change the color for convenience and understanding. Okay, right? So it comes out to be nice sinusoidal color. Okay, right? So I'm sorry, I need to draw that neatly. Okay, yeah, something like that. Okay, when you square the h of x, you are getting f of x. So h of x is a wave function of the electron. Okay, I'm connecting to the previous class. It's a wave function of the electron. Okay, so for us, wave function is written as psi of x. You take absolute square of x, you get f of x, which is the probability of finding the electron in the box. So we're calling as a probability distribution. Okay, the probability is distributed. You see, the overall probability of this electron, if you sum, it should sum to 1. What I mean is, if it's an increasing function, you see, f of x is continuously varying function. You take absolute square and you integrate from x is equal to 0 to x is equal to 1, you get a 1. Okay, x is equal to L. So this is completeness of probability distribution. What I mean is, probability should sum to 100%. Okay, so this is a material scenario. Okay, so let me go back to my black color marker. So electron is a material. Okay, shows wave nature as it is microscopic. Okay, and that it is also substantiated or supported by and this fact confirmed by de Broglie. How? He gave an equation called de Broglie equation which connects the wavelength of this particular wave nature where the lambda is this. Sorry, the wavelength, de Broglie wavelength is equal to Planck's constant divided by mass into velocity. Okay, depending on the mass with what velocity it moves. This is the de Broglie wavelength, which means sure for sure the electron behaves like a wave or shows a wave nature. Okay, now that was the story when electron is behaving like a wave. Now the question is if I take a light, now question is consider light. What is the light, by the way? It is an electromagnetic wave. Okay, it's an electromagnetic wave. Electromagnetic wave. Okay, which has electric field and magnetic field inside that. Okay, right? Now we took particles, material. We saw the wave nature. If you take a wave wave, do we see when we consider electromagnetic, do we see particle nature? Okay, or material nature? Answer is yes, absolutely. Okay, right? So the electromagnetic wave is made up of electromagnetic wave is made up of or consisting of the particles of energy which is photons. Photon. We know that with the Planck has given that idea, which in fact allowed everybody to explain the experiments which were unable like become a puzzle in 1900. Those experiments were easily explained by Planck, as he gives energy of a photon is just a Planck's constant multiplied by frequency with light is coming. Okay, fine. Now photon is behaving like a particle. That is amazing. Okay, right? So how are we going to study this particle? How are we going to understand this particle? So what we'll do, we'll take a page from how it is being understood, in material science. Okay, how particles, microscopic particles are understood in the material science, how it is done. Can we do that same thing in the case of photons or electromagnetic wave? Okay, right? So yes, what we'll do, we just question or ask how, okay, microscopic particles, how microscopic particles, okay, are dealt with, how it is dealt with, how they are dealt with. Okay, right? Now that's fine. If I want to know, okay, so let's ask them, the material people who studies them. And fortunately, what they will say is, okay, not only with us, right? Not only with us, every science you take, okay, right? In every science, right, there is something called vibrations or oscillations are involved. Okay, let me make a bold statement. The statement is, in every science or every branch of science, okay, every branch of science, okay, there involves vibrations are oscillations, oscillating phenomena. Okay, right? It involves. So they are saying whatever method which we are using, not only useful for material study, which could be used anywhere else, wherever there is a vibrations. Okay, right? So first of all, in the material case, what are the vibrations involved? Let me find out. Okay, so in the material case, as we have just saw, the right, so electron which is oscillating like vibrations. Okay, the electromagnetic wave is oscillating. Okay, but when it comes to material, if I just take a nucleus, electron around the nucleus like a hydrogen atom, there electron is making on oscillations. It is going round and round about the nucleus. Okay, so what is that? It is equivalent to a simple pendulum making oscillations from, let's say, left side to right side. Okay, so it is continuously oscillating. Fine. So left side point to right side, it is oscillating. Let's say it starts from left, go to all the way to the right, and come back to left. It is making one complete oscillation, similar to electron is rotating about the nucleus, one complete rotation. So that is there. And simple pendulum is a classical mechanics object. Okay, right? So in the case of statistical mechanics, okay, so thermodynamics, probably something moves. If you take a glass of hot water, okay, and if you heat it, if you say the particles rotate from bottom to top, it will go and then it will just using bubblings. Okay, right? It is there in statistical mechanics, solid state physics, and atomic and nuclear physics. It is there anyway, and even in the inside a atomic particles, there is something called particle physics. So everywhere these vibrations are involved. So the examples are in every branch of science. It is there. Now I can give a list of examples or the more list of branches where the vibrations are involved is classical mechanics. Okay, right, and electrodynamics. Okay, and statistical physics. Fine. Okay, let me reduce the thickness little low. Yeah, statistical physics, it's too low. And solid state physics. You see, if I keep going listing, I get as many as possible. Atomic and molecular physics. Atomic molecular physics. I'm just listing in the branch of physics itself, and particle physics. So vibrations are there. Okay, particle physics, right? So it is there everywhere. So better we understand what is this. Okay, right? Now, how it is done, dealt in the case of material sciences. Okay, so they are going to study. They are going to study in terms of quantum physics rules. So actual study involves quantum principles. Okay, so what is this quantum principles are? Okay, let's say if there is an object M, okay, if there is a microscopic an atom or an electron is there, okay, an object of mass M, if it is there, what happens? It is moving, it is going, if moves M and moves with velocity v, which implies it is going to have a kinetic energy of mv square. Obvious. Okay, so probably what we do, we multiply it by m divided by m. I'm going to get a kinetic energy Okay, m square v square by 2m. So I'll introduce linear momentum, which is to be p square by 2m. P is mass into velocity, linear momentum. Okay. Now, as we know, in quantum mechanics or quantum principles, the momentum becomes a momentum operator. Okay. What is that? So, P is represented as linear momentum. I'll call it linear momentum, represented as or takes a form of momentum operator P hat. Okay, and mass is just a number, it remains the same. And let's say the object is moving with some position in the direction of x, so it takes a position operator. Okay, and position is represented as position operator. This is a momentum operator. Okay, this is position operator. Now I know for kinetic energy. I want to also know what is the potential energy of the system. I want to know that. Now, since something is oscillating, it is just like a spring mass system. Okay, what I mean is something oscillating or vibrating is equivalent to spring mass system. Okay, right? What is that spring mass system is? We'll have a spring, okay, and there is an object of mass m. So if there is a displacement of mass along the up and down, so I'll have oscillations. So here let's say spring constant is some k. Okay, k is a spring constant. So what I'll do here, what I'll do, as see, initially the object is at some height and then it comes down, it's moving up and down. So its potential energy, the potential energy of the object is keeps changing. How it is changing? Is changing, okay, with respect to position. Okay. So what I will do, we can show that rate of, see, if U is a potential energy, okay, then the rate of change of potential energy with respect to position is going to be equal to, okay, so that rate of change of position is equal to the force exerted, force applied, okay, to create the oscillations, okay, to force applied to create the oscillations. Okay, by the way, who is creating the oscillations? Somebody who is trying to pull down, they are creating the oscillations. Now, when you try to pull down, what happens? When you try to pull down, the spring is not allowing to get back, actually, allowing to pull down. So you have to exert some force. So that force is consumed inside the spring, and that is actually spring is going to exert a restoring force on you. The opposing force, how much opposing force it's going to exert? It is going to exert a restoring force, restoring by spring, is equal to, let's say spring constant is k, and let's say I have created a like spreading. Okay, if I'm going to stretch by x, so k into x with a minus sign is a force. Remember, even the rate of change of potential energy is also try to oppose this force. So there is a negative sign here, there is a negative sign here. Okay, I just found out that the force is minus of kx. Let me write down the overall equation, which is equal to k into x. If I consider both the negative signs, they get cancelled. So this is I have. Now what you do is, let's arrange the system into such a way I can solve it. So I just rearranged so that I can solve it. Now I just integrate from where? From x is equal to 0 to some x is equal to L. Okay, right? So for otherwise, what you do, you can just leave without putting any limits. And then what I mean is, you are going to get potential energy as a function of x, which is half k x square. If you integrate, this is what you are going to get. Very good. I just got what is the potential energy of a spring mass system. But the question is, in my vibrations which I have considered, electron rotating around a nucleus, we don't have a spring. We don't have a spring mass system, but it is doing oscillations. Now I want to know, in place of kinetic energy, how should I represent my electron kinetic energy? Luckily for us, there is a method. What is that method? Is, okay, right? So let's say I have a spring mass system. So let's say I have a bowl. Let's say some electron kind of a marble is going up and down making an oscillations. There is no spring involved here. Okay. Now let's say the position change is, okay, if the object, okay, let's say a marble inside a curved bowl. What I'm doing, I'm trying to replicate electron motion as marble inside a curved ball. Okay. Now, as we know, Newton's second law says F is equal to ma. If there is a force acted on the system, it creates an acceleration. What is this? Which is equal to mass into rate of change of position. Very good. Okay. Now, F is equal to ma. If I try to create an oscillation, there is a stable situation for the marble here, steady state situation, means equilibrium position. So I'm just going away from the equilibrium position and creating the disturbance in the system. It is also called perturbation. Okay. So system is going to oppose that kind of a motion with some spring constant kind of a thing. So what I will do, I'll say the opposing force by the system is something like minus k x. How much disturbance you are going to create, that much of a spring opposition force I'll get. But right now I don't have that spring here. But I will say it is opposing force. It's just like a spring constant. Okay. Now if we just take this final equation, which is m rate of change of position in second order derivative plus kx is equal to 0. Okay. Now just to do the rearrangement, send the mass, like divide the mass by entire equation. Divide the entire equation by mass. What do I get? I get derivative of second order position x, k by m x. Okay. So this is second order differential equation. Second order linear differential equation. Okay. You can just straight away guess the solution for this differential equation by putting solutions. Could be simply, you can just check x is x naught sine omega into t. Okay, where omega is, okay, square root of k by m. Okay, what I mean is, this equation, in this place we have omega square. So for, if you resubstitute this, this is going to satisfy. So therefore, these are the solutions for the differential equation. Now, what I got, omega with angular, with what angular frequency it is making oscillation is dictated by spring constant. I don't have a spring constant here. There is some kind of a restoring force comes out of this system, a rigid force, opposition force comes out of this system. because no system wants to disturb from its stable state, right? If somebody was sitting quiet, okay, if you go and disturb, they don't like it. So they oppose that disturbance. Same thing here. There is a equilibrium position, okay, for the marble. Okay, you are disturbing that equilibrium position. So it opposes you. Now I want to know what is that opposition force. If at all, if there is some kind of a spring constant, what would be that spring constant would be? Just now I found omega equal to square root of k by m from the differential equation. Okay, so I can simply get omega square is k by m, which implies the spring constant, if there is any, for a particle in the marble, sorry, a marble kind of a particle oscillating in a dish, and its spring constant would be mass multiplied by with whatever angular frequency it is making oscillations. By the way, what is angular frequency? 2 pi into just a frequency. Okay, let me write a mu here. We did use f already notation, so just to avoid the confusion, let me write a mu. It's a frequency. Okay, means how many oscillations it make in a given second. If I multiply it by 2 pi, it becomes how many cycles of oscillations, how many rotations it making in a given time. Okay, that is what 2 pi into mu. Fine. Okay, now if you see, I just got what is a spring constant. Therefore, the spring constant, if there is any for, okay, for a microscopic object with mass m, okay, if it is making oscillations or vibrations, so that spring constant would be k is equal to m omega square. Very good. I just got what is a spring constant. Now, why do I needed a spring constant? I needed a spring constant to write the potential energy of this microscopic particle, which is making a oscillations. So straight away, so knowing the spring, see, knowing the spring constant, what I can do? I can write the potential energy of the system. Potential energy. Let me confine to 1D, one dimension. So, by the way, potential energy is half kx square, which implies, which is equal to half, in place of k I will put m omega square x square. Very good. But remember, but in quantum level or at quantum level, okay, position x becomes a position operator. Okay, position operator, which is simply put a hat on the top. Okay, so simply position operator. So therefore, what is the kinetic energy operator? Sorry, potential energy operator. Okay, which would be half m omega square x square. Okay, now I know what is the kinetic energy, potential energy of the system. Earlier we got a kinetic energy of the system, which is p square by 2m. Okay, by the moment you know total, kinetic energy plus potential energy, you can write the total energy, okay, of the system of a microscopic particle, okay, microscopic particle like an electron making oscillations. Now I'll not call that energy anymore total energy. I'll call it as, that is called as Hamiltonian of the system. Okay, so what is that Hamiltonian? Let me put H at is equal to p square by 2m plus half m omega square by x square. Okay, so this is a Hamiltonian. Now, having known the Hamiltonian, what I can do? So there is a way. The moment you know the Hamiltonian, okay, Hamiltonian is like a matrix, but here I am giving as an expression, okay, right? So let's say if I know H as a matrix, means the information of the system and its surrounding represented in terms of matrix covering the system and its surrounding or environment and its environment, okay, then what I will do, then I will solve, okay, eigenvalue equation which is H, okay, H psi is equal to E psi, okay, if I know H. And in this particular case, okay, E can take an operator form. So here the E takes operator form. How? It takes operator form IH cross dou by dou t, time derivative. Okay, that's fine. Okay. So let's say if that gives a E takes operator form and we get time dependent Schrodinger equation. Time dependent Schrodinger equation. Okay, just a differential equation in time, just like Newton's second law, which is involves a spatial derivative. Okay, that is kept aside. Let's say if I know H as an expression, how should I solve that? Okay, so if I know H as an expression, let me write down the eigenvalue equation not in Dirac notation. See, this is in Dirac notation. This is in Dirac. Dirac introduced the Ket notation. In the Ket notation, but if I know H in H, okay, let me write a calligraphic H. If I know H in expression form, okay, so what I will do? I will write the eigenvalue equation now just without considering in Dirac notation. So here you see the wave function takes an expression. Wave function for me was it's like a sine wave or cosine wave or something. Okay, right? So sine or cosine wave. So let me write down explicitly p square by 2m plus half m omega square x square. Okay, remember, since we are wrote in terms of uh, uh, generic way, so this is a 3D, okay, into 1D. What happens? I'll have, for the simplicity, I'll just take 1D. Okay, right? So what I'll do, I will, when I'm writing a position operator, momentum operator, what I mean, momentum in x direction. So that is P becomes minus IH cross dou by dou x, operator form. Okay, right? So which means the Hamiltonian multiplying onto the quantum state is equal to energy value now takes just a number. It is no more operator. You know, I have already expressed the E in an expression form. Accordingly, E also, see, Hamiltonian is in the expression form. E also, accordingly, it's written. So here is a number representing energy of the system. Okay, energy of the system. Okay, fine, very good. Now, if you just to take this differential equation and explicitly write down position, remember, okay, the momentum operator is there, position operator is there. So explicitly, I want to put a momentum operator in its perfect form. So p square by 2m would be minus, okay, minus h cross by 2m dou square by dou x square. You know, If you just square this, you would get that minus h square dou square by dou x square. Okay, plus half m omega square. Okay, so x operator becomes small x operator. Okay, so x operator could be a r vector, but here I am going to one dimension, so I am just kicking x operator as a okay, let me not do it right now, so let's keep it as x operator itself. Okay, right? So fine. Okay, so x square, right? Psi of x is equal to e of x, e psi of x. Fine. Okay. Now this is a second order differential equation. Okay. So very, very difficult. Second order dA involving, okay, involving many parameters. Okay, so people say it's not difficult, but sorry, it's not impossible, but it's difficult to solve. Okay, so what we can do, as it is complex to solve as it is, okay, so it's better to choose some algebraic method. Okay, some algebraic, okay, method. Okay, what is that method is? That's algebraic method is, let me choose a conversion of the involved operators. You see this equation. Okay, if you see this equation, so there is a p involved. Okay, there is a capital P, capital X involved. Okay, so if you introduce, okay, algebraic method by introducing a conversion technique, which is small linear momentum or some other linear momentum, which is a scaled version of P divided by square root of mh cut omega. I'll tell you why this is being done. Why it is being done is, if you notice, P linear momentum is actually Hermitian operator. Means you just take a complex conjugate and a transpose, it remains to be same. There is no complex terms involved. So P is a Hermitian operator. Similarly, if you introduce Q operator. So what is I'll introduce a Q operator, which is a scaled version of position operator, where instead of dividing, I will multiply it by m omega. Okay, let me neatly write. I'll multiply it by m omega by h cut this time. Okay, so here Q is equal to Q dagger. So both are Hermitian operators. Hermitian operators. I introduced Hermitian operators. Why did I do? I want to just simplify the eigenvalue equation, which is involving second order derivatives. Okay. The moment you introduce this, what it implies is, what would be the p square would be? P square would be small p square m into h cut omega. Okay, you just see this. Now, what is the q square? Q square, capital P I am talking about. What would be the q square? Okay, sorry, what is the x square? I'm sorry, I made a mistake here. I introduced. Have I done correctly? Yeah, I have done correctly. This side it is a q, this side is x. What is the x square? Now I have to make a x square. What is x square? X square will be q square, okay, h by m omega. Okay, h by m omega. You got a conversion factors. conversion methods. Now what you do? Introduce them into H. Okay, introduce them into. Okay, yeah, fine. So introduce them into the eigenvalue equation we had earlier. What is that? This eigenvalue equation. H is equal to E rho E sine. Okay. So when you introduce, first of all, what happens to the Hamiltonian? You just see Hamiltonian is earlier p square by 2m plus half m omega square by x square. Now what happens? In place of p, I am writing small p square m h cross omega by 2m plus half m omega square. In place of x square, I'll put small q square h cut divided by m omega. You will understand now why did I introduce this kind of a conversion factors. If you see m gets cancels, m omega 1 omega and m cancels. If you get what you get, if you take a common, there is h omega is common, 2 common. What you got? You got, let me don't use a rectangular bracket, let me use a regular brackets, which is p square plus q square. You see, Hamiltonian become very, very simple the moment I introduce this kind of a conversion. Okay. So the conversion in terms of the Hermitian operators with the scales. Okay, this is algebraic method. That is what we usually do. Now, if you notice this expression, what expression? H psi of r is equal to E of r with this new term. What is the new term? New term is h being, okay, h being p square plus q square multiplied by h omega. But still the question is, I am not able to solve this. I am still not able to solve perfectly. Okay, I'm not able to solve this perfectly. So is there any other way I can much simplifies this? Okay. Earlier I tried introducing Hermitian operators. Now let's do second stage. Okay. My target is to simplify so that I can solve it. Okay. Now introduce non-Hermitian operators. What are non-Hermitian operators? Let me tell you. Hermitian operators. Okay, what are non-Hermitian operators are? A is not equal to A dagger. They are not complex conjugate. So these non-Hermitian operators constructed from P hat and Q hat. How I am going to construct? Let me call a new non-Hermitian operator. Small a hat is equal to square root of half. Okay, Q plus IP, right? If see, you take a dagger, which becomes half square root Q minus IP. Q and P anyway Hermitian, so I don't even bother writing Hermitian hat for both Q and P. Now you see A and A dagger I got. Okay. Now what you do is just take a dagger product. Okay, which is going to be 1 by 2 Q minus IP, sorry, Q plus IP, Q minus IP. Okay, so which is half into Q square plus P square plus I into PQ minus I into Q minus I into, okay, what is this? Yeah, Q into P. Okay, I made a mistake. Okay, first one is Q into Q into Q square, Q into Q into P. Q into P is a positive, but P into Q is a negative. Okay, Q into P is positive, P into Q is a negative. Okay, that is sure. Okay, right? So that is what we'll get. Q into P is positive. Okay, now if you see, take this, write down Q square plus P square, take I common, what you get is QP minus PQ. So there is something called commutator bracket. Commutator bracket. I think we checked it last time. What is the commutator bracket is? A comma B is AB minus BA. It is a commutator bracket. So while deriving uncertainty principle, we saw this. Now, what is the commutator bracket between Q comma P? Which is going to be QP minus PQ. So that means I have a commutator bracket here. Okay. By the way, what is a commutator between Q and P? You can find by introducing the proper expression for small p and Q and P. What is that? What is the X? So what is the Q, by the way? Q is square root of m omega by h cut into X minus 1 by square root of m omega h cut into P, sorry, capital P. This was the actual Q and P. You see, go back, see, right? Small p and small q, whatever I introduce, the same thing I'll substitute it here. By the way, what is P? P is minus IH cross dou by dou x. Okay. So if I do this, and x becomes just a simple x. Okay. Quantum mechanic operator forms, operators. Now, what do I get here? Okay, so this one into this, so which is going to be m omega by h into m omega h within the square root x into p minus, I'll take that comma, p into x. By the way, m omega cancels, I'll get 1 by h. Correct. Okay, very good. Now, what is this quantity? This quantity is x into minus IH cross dou by dou x. It is acting on 1 minus IH cross dou by dou x. It is acting on x. So this was the expression. Now, derivative of 1 is 0. Derivative of x is 1. So what I get? IH cross minus of minus plus IH into 1. So which is I. HH cancels. I'll get Y. So therefore, the quantum commutator between small q and small p is I. Okay, we got that. Now let's get back. Why do I need? I need to find what is the product of A into A dagger. So product of A into A dagger is equal to, okay, half q square. Okay, let me use regular brackets. We reserve rectangular brackets for commutator. Q square plus p square. And what was the expression? I into commutator bracket. I into q comma p commutator. So this was the product of non-Hermitian operators. Just now I found it is an I, right? So let me introduce of q square plus p square. Okay, the thickness got too low. Okay, not that much. Yeah, q square plus I into another I, which is half q square plus p square. Okay, minus 1. Right? So what you will do? Right? What you will do now? Q square and p square, I just got as in terms of A and A dagger. How? So You just 1 minute. There is a half where the half is coming. Okay, right? Yeah, right. Half is here. Let me have half into q square plus p square is equal to a dagger plus half. I can write that. Okay. By the way, what is my Hamiltonian? When you recollect, what was the Hamiltonian? When introduced, this was the Hamiltonian, which is Hamiltonian is half into h cut omega p square, okay, q square plus p square. This was the Hamiltonian. By the way, I found what is a half into q square plus p square. So can I just introduce this? So I'll get Hamiltonian in terms of non-Hermitian operators as half into a dagger. See, things become much more simpler. Okay, so let me introduce now. Let's introduce a n operator which is equal to a into a dagger. You know why? You just take a n dagger which is a dagger into a dagger whole dagger, which is going to give you a dagger whole dagger into a dagger. Just a matrix cases. So we'll get a dagger into a dagger which is equal to n. We can say n operator, capital N operator is Hermitian. So therefore, a Hamiltonian is having h omega half plus n operator, Hermitian operator. Okay. So inside a Hamiltonian, there is a Hermitian operator. They call it as a number operator. Okay. Now you see, I simplified the Hamiltonian to a very simple Hermitian operator, single Hermitian operator. Okay. So what we'll do, we'll discuss the implication of the number operator coming inside the Hamiltonian in the next half. Okay. So we'll just quickly take a 5 minutes break and then we'll just continue from there. Okay. Right. Yeah. So don't worry, I'll be sharing the entire notes so you can understand this by following through. Okay. So let's take a 5 minute break.